So this is a good point. Lightning carries thousands, 10,000s of amperes, while in our nerve cells that electrical conduction is microamperes. So as electrons undergo elastic collision, which means they will rebound at the same speed, but the direction will be different, and overall the direction will be random. So all the average velocities cancel out. The average velocity will be 0. But when an electric field is applied, they all drift along the same direction. So current is. This dielectric will contain positive and negative charges, which will approximately create a uniform field along the wire. This is similar to electrostatics. Actually, there is no difference between electrostatics and the current flow, because it happens very fast in statics. The electrons move to neutralize the electrical field very fast, but the batteries will keep supplying charges, so it just happens continuously until the battery runs out. So that's the same. This is just 10th standard basics, so no problem. Now this is the 12th standard Ohm's law. So E is the Jp, that is resistivity into the current density, or J is equal to rho E, which will be conductivity. That's it. Now we'll go into the collisions of the electrons. So there are n electrons with velocities vi, and when we take the average, we sum the velocities, the average will be 0, because obviously their directions are random. Now when field is applied, there will be acceleration of the electrons opposite to the direction of the field. So every electron will have the Vi, the capital Vi here, which will be V is equal to U plus AT. So U will be the Vi, the initial velocity that we saw here when the field was not applied, and then minus E by M, the acceleration, and Ti. And that would be the time elapsed since the last collision, the Ti since the last collision. And we should note that this is not the electrons colliding with electrons. This is rather electron colliding with the positively charged metal ions in the lattice. That's when it rebounds with the same speed, like the ball in the wall case. When it collides with another electron, it's just the other electrons move with the velocity. They exchange velocities, but that is not the case in conductors. So if we take the average of the cap Vi, not the small vi average would be 0. Cap Vi, we get the drift velocity. The average would be averaging this and averaging the time. The average time would be the relaxation time. That is the average time between successive collisions of an electron. So as we can see from this figure, the normal B line represents the motion of the electron when the field is not applied. But when the field is applied, it slightly deviates from its position, and we can see the B and B dash, which is B dash is like moving opposite to the electric field. That is exactly why we know that field force experienced by electron will be opposite to the field direction. So this is very unique because the average velocity of the electron does not depend on time. We saw this that this velocity is superposed over the average velocities. The drift velocity is superposed over all the random motions of the velocities. Like it is the net result. So there will be a current. And this Vd. Let us write in the equation using the fact that current into time is the charge carried. So the N is the number of electrons per unit volume, and minus E is the charge of each electron. So per volume there is n electrons. So the total charge is minus Na, and then this is volume. So Vd into T would be the distance covered, and A is the area. So per volume and the actual volume cancel out, and this is the charge transferred to the conductor in time interval T. So this T and this T cancel out. I is equal to NE Vd. That's actually the opposite. So we already know from that drift velocity derivation minus En by m t. Just substitute this here. Pi delta t is equal to plus m e a. So this a comes here, e square e by m tau. So there is this Ia, which will be J net So what relations do we have now? We know the basic relation will be V is equal to IR. So V can be written as E into L, and I can be written as current density into I into R. So R is rho L by A, and the current density has that A, so I by A becomes the current density. So E is equal to J vector P, that is the field and the current are in the same direction, or J is equal to conductivity into E. So this is one relation. Now we average that drift velocities. That will be V is equal to minus E by M into tau. And what else do we have? So we can use the fact that I into del time will be the NEA Vd into dt, and from Vd equation that we derive minus E by M and tau, that we can substitute here. And then what do we do? We use I is equal to J, the current density definition, and substitute that too. And we have another relation for J and E, which we compare with the earlier Ohm's law equation, and we get that conductivity is Ne square by M into tau. So you can see all of them are constants. That makes sense. Okay, so this question, estimate the average drift speed of conduction electrons in a copper wire. Okay, so we have the area, we have the current, we have density and atomic mass. So first we find out the number of electrons per volume. So number of electrons per volume, we have density. So we know that 1 mole, that is 1 mole 63.5 gram, will give us one copper atom donates 1 electron. It has 6 into 10 to the power of 23 electrons. Now if we find, we have mass, we have density, just find out the volume. So 63.5 gram and the mass by rho by 9 into 10 to the power of 3 kg will be the volume, which contains 6 into 10 to the power of 23 electrons. So we have drift velocity of order millimeter per second, 1 millimeter per second. So the average speed that copper has, that itself, the copper itself is very solid, so it only vibrates, but that itself has 200 meter per second. And then compared to this, the drift velocity is very very small, 10 to the power of minus 5 times at ordinary temperatures. This field, even though the electron speed is very slow, there are like infinite number of electrons which can form a current as instantaneously as the electric field is applied. So let us try these questions. So all of these questions are right. So and we have to note that in the copper example the current was 1.5 amperes, so obviously the speed would be small. So with for large currents the speed will be much larger. You can see as in this example. So almost the instant the current is established, because instantaneously they just have to move from their position. So not a single electron can travel through all the wires. Only the instantaneously there will be displacement, but it still takes some time to reach a steady value. But force should cause acceleration. For B question, the acceleration, it is accelerating, but it gains velocity, then it collides, and then it loses velocity. On an average, they acquire a drift speed. A large amount of current can be obtained because there's a large density of electrons in the conductors. For D, no, absolutely not. They collide, and this only in a random path. Only in the average path they move from lower to higher potential. So from our electric field, we know that when we release an electron, it covers a parabolic path or something. So in presence of electric field, their paths are curved, but in absence, they are straight. Collision, normal collision. So mobility. So we can just revise this once. In metals, the mobile kinds of carriers are electrons. In ionized gas, we know cathode rays and anode rays. The cathode rays are probably the electrons, and the anode rays are gases, positively charged ions. In electrolyte, it can be positive and negative ions. We know this. Ionized gas is something we need to revise. So mobility is defined as the magnitude of the drift velocity per unit electric field. Magnitude, so ignore the direction, because obviously mu is a scalar quantity. So practical unit is centimeter square by volt. Let's just derive this on our own. Vd by E, and we already know that Vd, magnitude of Vd is E tau electric field by M, and we substitute this, so E tau by M. The practical again meter square by velocity second, volt second, and cm square by volt second is a practical unit. Now this is important, all these graphs are important. Let's just do this. So limitations of Ohm's law. The deviations of Ohm's law are broadly of three types. So A simply does not follow the linear relation, V is directly proportional, right? Second, if usually we apply potential in one direction, the current will be in that direction, and if we reverse the voltage, the current will be in opposite direction of the same magnitude. But this does not happen in case of diodes. Practical was also based on this, and the relation between V and I is not unique. So this is kind of complicated, because for the same value of current there are various voltages, or for the same value of voltage there are various currents. We can draw a line here, which is only for same value of current, there are different voltages, gallium arsenide, one of the best semiconductors, is always even in solid state. So you can see from gallium arsenide, the voltage current is in milliampere, obviously, and first it follows a linear relationship, and then it becomes non-linear, and even more shocking is the negative resistance, not necessarily because it is a semiconductor after all, so it's a curved one. And diode, this diode graph I have seen 1000 times. So even though this graph curves a bit, it is a good conductor, because practical cases it can only be like so, not so accurate. So these are all resistivity of conductors. The chrome, okay, so let's just write this equation, because we are rho is equal to rho naught 1 plus alpha dt. So rho minus rho naught will be the dp, rho alpha delta t, so d rho by dt 1 by rho. Okay, this is the temperature coefficient, just to make it clear. So semiconductors have a negative resistance. Silicon has the highest negative resistance. Yes, this is what we were looking for. So there are two types of commercially produced resistors for use in laboratories and home purposes: wire-bound resistors and carbon resistor. Wire-bound resistors are made of alloy, winding the wires of an alloy, that is nickel, manganese or constantan, or similar things. This because their resistivity are not very much dependent on temperature. That's why they are also used in the potentiometer this experiment, manganese. So these resistors are typically in the range of a fraction of an ohm to 100 ohms. 100 ohms, because we don't need so much ohms. So resistors in the higher range, because obviously these are metals, carbon is a non-metal, it will have a higher resistance, so they are very small, so that's why the need for color coding. So let us just say this once again. B E Y, Great Britain, V G W. So in the order, in the alphabetical order: black, brown, red, orange, yellow, green, blue, violet, grey, white. So gold, silver. Gold is 5, silver is 10. Somehow I remember this, I don't know. Also, you could see that once again. Somehow associate copper with the number 10, and gold is also under copper in the same group as, silver is also under the same group as copper. So consider AG as 10 and AU as 5, and no color means 20% tolerance. So black, BB Roy of Great Britain, that mnemonic you can use. But just remember, gold is 5, silver is 10, and no color is white. That is the tolerance. So this is the graph that we asked in NEET 2020. So this copper has higher resistivity as temperature increases. That obviously is a metal. Okay, so nichrome wire is used in experiments because it has very less dependence on temperature. As you can see over, this is 0 to 800 plus Kelvin. There is only a change of 0.1 micro ohm centimeters. So that is very, very small, and it is approximately very constant here. So that's why nichrome is used. And semiconductor, obviously, with the decrease in temperature, the resistivity decreases. Just note the values. For copper, the resistivity is of the order ohm meter 10 to 25 minus 8. That is pretty small. So this too the same, because resistivity mu is 10 to the power minus 6 and centimeter 10 to the power minus 2. So same. Copper goes from over a range of 150 Kelvin. Copper goes from 0.0 to 0.4, but over a range of 800 kelvins it only increases by 0.1. So they are wire bound resistors. Okay. So let us understand why resistivity increases with temperature. So we know that resistivity is 1 by conductance, which we derived earlier, where we used the Ohm's law equation and the velocity. We combined all three equations: the drift velocity, the Ohm's law equation, the vector form of Ohm's law equation, and the I is equal to NEAV. All we combined and found that conductance. So if we increase the temperature, the collisions will become more frequent. That means the relaxation time decreases. If relaxation time decreases, the resistivity must increase. So this is in the case of metal conductors, but for insulators and semiconductors, there is negative dependence with temperature, because when you increase temperature, more number of electrons start participating in the conduction, and this will outweigh any increase in, any decrease in the relaxation time. So insulators too have a negative resistance coefficient. So there is literally no difference between the resistivity and the resistance temperatures with, the relations with temperature, because for the same material, for the same resistor, you know that just multiplying L by A will give us the resistance. So both are the same, so don't get confused by that. They don't have separate equations. On heating, the resistance increases and current decreases. That is example 3.3. And this is like literally thermal chapter. So let us review this. So electric power means that so the electrons lift from lower potential to higher potential. That means they are losing electric energy, losing electric potential energy. Let's just derive this. Del Q, they are moving from A to B. That means just consider current here, not electrons. A is at higher potential than B, which means VB minus VA will be negative, minus del Q B, which is the change in potential energy. This del Q B will be less than 0. That means if del U is decreasing, so decreasing means that energy should go as kinetic energy, the change in kinetic energy, but on an average the electrons do not gain any velocity. They don't change velocities, only the drift velocity is there. So half mv square will be the velocity even after losing going anywhere. So this change, loss in potential energy, goes as heating. So what exactly is this heating? They collide, right? So when they collide, the electrons hit the atoms, and the atoms start vibrating more, and that results as heat, increase in temperature also. This is also called Ohmic laws. So where this energy, the power work done comes from the battery, the cell, chemical energy of the cell. This we have learned earlier. We try to minimize current heating effect due to current by increasing the voltage. So we know that P is equal to 8. Let the connecting wire have a resistance C. The power dissipated will be PC into I square RC. I will be V square by V square RC. So what exactly is this? Wire goes to, here we need power P. That means to get the power P here, it should have traveled it should have traveled through a potential V with current I. So this is the power to be delivered at the station where we actually need it. So through the wire we will connect the power dissipated, the heat dissipated. So PC is equal to VC IC. Let's try. So VC into IC, VC would be the IC would be VC by R. Because the current will be same throughout, so I square RC. And I is P square by V square RC. So these are constants. This is determined by the power required at the station, and RC is constant because wire resistor. Now PC is the power dissipated through the wire, and V square is the voltage across the wire. To increase the voltage, the power dissipated through the wires would be very small, so that's why you should not touch the transmission wires, so you'll get a very nasty shock. The positive electrode will have a positive charge with respect to the surrounding solution. The negative electrode will have a negative charge with respect to the surrounding solution. And when there is no current passing through, the potential will be same throughout, and the potential difference, the E electromotive force would be Vm minus Ev.
So the relation between EMF and voltage, voltage means terminal voltage. Terminal voltage we'll denote it with V and EMF will denote it with E. Now, you see, let us take an example of a positive charge, let us say. So if I start for a positive charge, I can think that okay, H plus has broken from here, SO4 is over here, right? So H plus, EMF will denote it with E. Now, you see, let us take an example of a positive charge, let us say. So if I start for a positive charge, I can think that okay, H plus has broken from here, SO4 is over here, right? So H plus starts from here, starts moving like this, correct? I am now thinking in context to motion of the positive charge. So this positive charge moves like this, although the positive charge is not moving, but you can perceive the motion of the negative moves like here. SO4 is over here, right? So H plus starts from here, starts moving like this, correct? I am now thinking in context to motion of the positive charge. So this positive charge moves like this, although the positive charge is not, for a positive charge, I can think that okay, H plus has broken from here, SO4 is over here, right? So H plus starts from here, starts moving like this, correct? I am now thinking in context to motion of the positive charge. So this positive charge moves like this, although the positive charge is not moving, but you can perceive the motion of the negative charge as the motion of the positive charge in opposite direction, okay? So then we can think of all this coming over here and then completing one full cycle, okay? The amount of work in doing so, in completing the full cycle, is called as EMF. The amount of work done in doing so is called as EMF, no problem. So EMF is the total work done to complete this full cycle, no problem. Now, the terminal potential is the amount of work done in going from one terminal to another terminal, one terminal to another terminal, okay? So let us say we say that this amount, so the amount of work done in going from one terminal to another terminal is equal to V, right? So the amount of work done in going from one terminal to another minus IR. VA minus VB is nothing but voltage, will denote it with V and EMF will denote it with E. Now, you see, let us take an example of a positive charge, let us say. So if I start for a positive charge, I can think that okay, H plus has broken from here, charge, let us say. So if I start for a positive charge, I can think that okay, H plus has broken from here, SO4 is over here, right? So H plus starts from here at terminal voltage. Terminal voltage will denote it with V and EMF will denote it with E. Now, you see, let us take an example of a positive charge, let us say. So if I start for a positive charge, I can think that okay, H plus has broken from here, SO4 is over here, right? So H plus starts from here, starts moving like this, correct? I am now thinking in context to motion of the positive charge. So this positive charge moves like this, although the positive charge is not moving, but you can perceive the motion of the negative charge as the motion of the positive charge in opposite direction, okay? So then we can think of all this coming over here and then completing one full cycle, okay? The amount of work in doing so, in completing the full cycle, is called as EMF. The amount of work done in doing so is called as EMF, no problem. So EMF is the total work done to complete this full cycle, no problem. Now, the terminal potential is the amount of work done in going from one terminal to another terminal, one terminal to another terminal, okay? So let us say we say that this amount, so the amount of work done in going from one terminal to another terminal is equal to V, right? So the amount of work done in going from one terminal to another terminal is equal to V, correct? Then how much extra do you have to do? How much extra work do you require? You require work from where to where? To move between the terminals, correct? If I is the current and R is the internal resistance, how much extra do you require? How much extra do you require? You require plus I into R. So what do you get? E is equal to V plus IR. And then if you rearrange this, so this is the relation between E and V, no problem. So you can clearly see that while discharging, the value of the EMF is greater than the value of the terminal potential when the battery is getting discharged. So you can write V is equal to E minus I times R. Okay, did you get this? All right. The total work done from this point to this point is EMF. Okay. Work done from this point to this point is V. So what will be the work done? Okay. Times R. Okay. Did you get this? All right. The total work done from this point to this point is EMF. Okay. Work done from this point to this point is V. So what will be the work done from here to here? So V plus IR. Did you understand? From here to here it is V. So V plus IR will give you EMF. V plus IR will give you EMF. Did you understand? Okay. So that's how you get this expression. V is equal to E minus IR, or even you can write E is equal to V plus IR, whatever it is. If you want, you can also use what? Kirchhoff's rule. You can also use simply Kirchhoff's rule. I'll show you even by Kirchhoff's rule, don't worry. Okay. Just giving you a feel of what happens. So for the entire cycle, the total thing is 100, let us say. Okay. If the terminal potential is 80, then how much extra do you require to move between the electrodes? How much? 20, right? So what we are saying is 80 plus 20 is equal to 100. Total work done is equal to 100. Moving between the terminals, that is equal to what? Externally I am talking about, right? That is equal to terminal potential. And then as you move between the two electrodes, that is equal to I into small r, because small r is the internal resistance, right? So the total work will be E is equal to V plus I into small r. As simple as it can be. Did you get a whole feel of this EMF? I'll also prove it by using Kirchhoff's rule, don't worry. Okay. Anyways, once we have understood this, we need to star mark one very simple formula, of course, and that is V is equal to E minus IR. What will be the value of V? Of course, V will be equal to I into capital R, because this is external to the circuit, right? So where I am assuming the entire resistance over here is equal to capital R. R is the external resistance. Small r, that is capital R, is the external resistance, and small r is the internal resistance. So I hope you have got